Equilibrium concentration calculations are something that are going to be really helpful to us. And we're going to look at a little bit of math in this section, so I'm just letting you know. But let's look at a typical set of calculations, things you might run into in problems like these. So this reaction is our H2 plus I2 making HI, and the K value we saw earlier, 55.3. It's products divided by reactants. We're going to square the HI, but the H2 and the I2 are the same. So let's say that we decide to do this reaction, and we're putting 1 mole of H2 and 1 mole of I2, and we're putting them both into a liter flask. We can use this information to calculate the equilibrium concentrations of H2, I2, and HI. Before we do anything, though, the value of K will tell us if our answers are going to be right or not. So in this problem, K is larger than 1. That means product favored. So when we go through the calculations here in a little bit, at the end, we should end up with more HI than we have H2 and I2. H2 and I2, the concentrations will be going down, and the HI concentration will be increasing. At the end, though, H2 and I2 will not be 0. All right, they're going to be some small number, but they will go down as HI is made. And at the end, we should end up with more HI than we have H2 or I2. So to solve a problem like this, set up the ICE table once again. And remember, ICE tables will be reactants on the left, products on the right. ICE stands for initial change equilibrium. So for this reaction, here's what I have set up, H2 and I2, and then HI on the other side. Now remember that H2 and I2, the reactants, are going to have a different change sign than HI. And in this problem, as we talked about, the H2 and the I2 will be decreasing, and the HI will be increasing. And the other thing about the change line is that the stoichiometry for this reaction will be evident in the change line. So for this reaction, that's 1 H2 and 1 I2 making 2 HI. Change here will be affected by that, and we'll see that. Now, initially in this reaction, we have 1 mole per liter of H2 and 1 mole per liter of I2, and we don't have any HI. Now, H2 and I2 are going to go down by some amount, and let's call it X, okay? And X is how much not only the H2 decreases, but the I2 as well. H2 and I2 both have a stoichiometry of 1. On the other hand, as they go down by X, HI is going to go up by 2x. It's got a stoichiometry of 2 relative to the 1 H2 and the 1 I2. So at equilibrium, we're going to have 1 minus x for both H2 and I2 and 2x for HI. So x here is just the amount that these things are going to change. We're going to do a problem here in a little bit where we're going to solve for x. So remembering here that the Kc value for this equilibrium, 55.3, we can set this up. 55.3 is K, and that equals the equilibrium concentration of HI, which is 2x squared. Remember that we squared it. So notice that that stoichiometry of 2 popped in 2 ways. It's the change, that part right there, and it's also the order. That's kind of cool. And then in the denominator, we'll have the H2 and the I2, and both of them are 1 minus x. So it's like 1 minus x times 1 minus x. You can imagine we can abbreviate that as 1 minus x quantity squared, which is kind of cool. And believe it or not, at this point, one equation, one unknown, x. And if we can solve for x, we've got this. In the old days, i.e. when I took this class basically, we did elaborate sets of algebra, all right, to figure out what x is. But I do want to point out that in this wonderful day and age of Google and all kinds of things, a lot of your calculators have a solve button on them. And man, oh man, I would have died for a solve button back in the day, okay? If you have a solve button on your TI or whatever kind of calculator you we've got. I really recommend you get it out and figure out how it works, because man, the solve button is going to make just nothing out of most of these problems, which is really, really cool. So if you have a solve button, I highly recommend that you learn how to use it, because it's going to be very helpful to you in Chemistry 223. On the other hand, if you don't have a solve button, there's nothing wrong with doing this the old school way. And I'm going to show you some tricks how this works. It's not a big deal. All right, you can do it either way. But if you do have the solve button, oh man, check it out. But anyway, I'm going to assume at this point that you don't have the solve button, and that's totally cool. In this kind of problem, what I would do is I would take the square root of both sides. All right, let me show that old equation one more time. Here it is again. Notice that it's like 2x quantity squared and 1 minus x quantity squared. So if I rewrite that, it would be 2x squared divided by 1 minus x squared equals 55.3. Well, in the old days, again, before the solve button, when I had to walk uphill both coming to and going from school, and etc. Anyway, what we would do is you can literally take the square root of both sides. All right, square root of 55.3 is just a number. I don't know what it is. I'll tell you on the next page. But here's the cool part. 2x quantity squared becomes just 2x. And 1 minus x quantity squared becomes just 1 minus x when you take the square root. So the square root kind of cancels out the squared parts right there. So this part right here is what you get when you square root it. Square root of 55.3, 7.44. And square root 2x squared is 2x, and square root 1 minus x quantity squared is just 1 minus x. So this problem now is just good old algebra. We got to get the x's on one side. We got to get everything on the denominator. We'll multiply both sides by 1 minus x. If you do that, you get 7.44 times 1 minus x equals 2x. 1 minus x divided by 1 minus x cancels. Then you get all of the distributive property. So 7.44 times 1 is 7.44. And then the same thing times minus x minus 7.44x equals 2x. Again, get all the x's on one side, so that would be 9.44x equals 7.44. X will equal 7.44 divided by 9.44, 0.788. Again, making sure that's very clear. At this step, 7.44 equals 9.44x. You divide both sides by 9.44. These numbers cancel. You've got just x. And this part right here, you can see equals 0.788. So this is how I would recommend doing these problems. But again, if you have that solve button, you'll get really nice problems out of it. Anyway, that's the x value. That's what we were looking for. So back to the equilibrium parts of the ice table, the H2 and the I2 were both 1 minus x. So 1 minus 0.788, we get 0.21 moles per liter. And HI was equal to 2x. So 2 times 0.788, 1.58 moles per liter. Now, these numbers might seem a little esoteric at first, like what do they mean, right? And I dig it. So one way to help you, remember, K is greater than 1, like 55.3, mean more products, HI, than reactants, H2 and I2. And lo and behold, you do have more HI. 1.58 is quite a bit larger than 0.21. That means you have more product than reactant. Oh, it's all coming together. So anyway, check this problem out. Taking the square root of both sides can be really helpful on some of these problems, just FYI. But also, if you have that solve button, do it. Here's another problem. N2O4 can be made into NO2, all right? And N2O4 is diatomic, you can argue, like a type of diatomic molecule, two NO2s. But they do make a stable bond, and it ends up making NO2. N2O4 is mostly colorless, while NO2 has kind of a brown color. So it's kind of an interesting reaction. Just be careful with it. In this reaction, N2O4 going to NO2 has been studied. Notice the stoichiometry of 2, K 0.0059 at room temperature. Now this K is much less than 1, okay? And K's less than 1 mean more reactant than product. So at this equilibrium constant value, you would expect more N2O4, the reactant, than you would NO2. And that's kind of a cool thing. And there's the Kc expression. Again, products divided by reactants, square the NO2 but not the N2O4, equilibrium constant, again, less than 1. So let's say that initially we have 0.50 molar N2O4. What are the equilibrium concentrations here? So in this K, which is less than 1, some of the N2O4 will make NO2. But because K is less than 1, we expect there to be more N2O4 at equilibrium than NO2. So to figure out what the actual numbers are, once again, let's set up that ICE table. We'll have the reactants on the left and the products on the right. Initially, 0.50 mole per liter N2O4 and no NO2. Now, N2O4 has a stoichiometry of 1 and NO2 has a stoichiometry of 2. The N2O4 will be decreasing by X. The NO2 will be increasing by 2X, 2 to 1. So at equilibrium, 0.50 minus X, NO2 will be 2X. Remember, the equilibrium means you must have reactants and products. So you wouldn't put like 0 for NO2 and then minus 2X. That doesn't make any sense in chemistry. No negative mass. You have to have positive reactant and product concentrations for all equilibriums, at least in chemistry. But anyway, in this problem, then the equilibrium, 0.5 minus X for N2O4 and 2X for NO2. So we can set up now the equilibrium concentrations equal to the equilibrium constant. The equilibrium constant, 0.0059. NO2 squared would be 2X. That's the equilibrium NO2. And again, you square it again. You do it twice. And then for N2O4, 0.50 minus X. So again, we have one equation and one unknown X. 0.0059 equals 2X quantity squared divided by 0.50 minus X. Now again, this is a problem where if you have that solve button, score, you're good to go. However, if you're like me, who doesn't always I feel kind of like still using the solve button is cheating, but I know that's old school and really silly. But anyway, if you want to do it the old school way, which is totally fine too, we need to rearrange this equation a little bit. So first we're going to get the 0.5 minus X out of the denominator. We're going to multiply both sides by 0.5 minus X. So then you have 0.0059 times 0.5 minus X, and 2X quantity squared becomes 4X squared. So you can see then in the second line there, 0.0059 times 0.5 is 0.0029, and then also 0.0059 times negative X, you can see that equals 4X squared, and you rearrange it to 4X squared plus 0.0059X minus 0.0029 equals 0. And if you remember from math classes, I've written it this way because this is the form you need for a quadratic equation. Now in a quadratic equation, you always have an X squared, an X, and just a number. And the numbers in front, like here, this 4, that's the A, all right? And 0.0059, that's the B term. And C here is negative 0.0029. So C is negative 0.0029. So if you have a problem like this, write it as a quadratic. Ax squared plus bx plus c equals 0. And here c is a negative number. That's fine. A can be negative, b can be negative, whatever. But we use these a, b's, and c's in the quadratic equation. If you haven't used the quadratic equation for a while, it's quite all right. The quadratic equation, x equals negative b plus or minus square root b squared minus 4ac over 2a. And literally the b, a, and c numbers are those numbers we just pulled out of the equation. So knowing that, we can put all of those things in. So negative b would be minus 0.0059 plus or minus square root b squared 0.0029 .0059 squared minus 4ac. So minus 4 times a, 4, times c, negative .0029. Got to do a little bit of math here, all right? But no problem. We need to divide everything by 8, the 4 times 2. And when you do that, you get here negative .00074 plus or minus. There's the 1/8, the 1 divided by 8. And all that stuff from parentheses, when you square root it, 0.046. Or actually 0.046 is the number, and then you square root that. Sorry about that. To the plus or minus part, plus or minus literally means you'll either add it or subtract it. So 1/8 times the square root 0.046 is 0.027. That's the plus or minus part. X is going to have two values here. In a quadratic formula, you're going to end up with two values of x. And so in this case, the values of x, one will be negative .00074 plus 0.027, and the other one will be negative .00074 minus 0.027. Those are the two allowed values of x here. The good thing about chemistry is that negative values of concentration and mass, etc., are not allowed. So when you actually solve for x, you get a positive and a negative number. Positive .026 and negative .028. Negative x's don't fly in chemistry because that would imply a negative moles, a negative mass, and that's not how chemists roll. So in a quadratic formula, the negative value is always thrown out. Only the positive value is allowed because, again, mass is always positive. So in this problem, x is the positive .026. And in the initial equilibrium values, N2O4 was 0.50 minus x, so that would be in this case 0.47. Remember that you cut the significant figures off at the hundredth spot, so you did exclude the rest of it. On the other hand, NO2 was 2 times x, 2 times 0.026, positive 0.052. Now, remembering that the equilibrium constant was a number less than 1, we predicted there would be more reactant, more N2O4 than NO2. And that's what we're seeing, all right? 0.47 is a lot bigger than 0.052. So reactant favored Ks, more reactant. N2O4 is certainly greater than NO2. In quadratic formula, all right, if you have a positive and a negative value of x, like here, the positive number is the one you want. You don't want the negative one. Negative mass doesn't fly. Some of the examples we're going to see, you'll end up with two positive roots, two values that are positive. And if you see two positive values, you want the smaller x. The larger x, when you plug it back into the equilibrium, will end up with a negative number. So FYI on that one. So again, when you're doing quadratic, positive and negative, always pick the positive. If you do end up with two positive roots, then you want the smaller of the x values.